And let's see if you guys have any questions on relative position. Anything in here give you guys grief? This is the stuff that, oh, I should pull this back a little bit. Charlie, you guys ever had Charlie in class before? Yeah. He's awesome. Calculus, yeah, he's a good dude. He's a good dude. All right, relative position, that's almost legible-ish. Anything in here give you grief? So this is what I'll put the quiz on for Monday, because we'll have a chance to ask questions you haven't. Please, Tabitha.
So when I started to make the ogive,
Yes.
I had the cumulative
Mm-hmm.
in L1.
Okay.
And then in L2 I put 1, 2, 3, 4, 5. Is that what you're supposed to
What data set are you using? I don't have the book anymore, so I don't. Was it a raw set of data, my friend? Were you pulling it from a raw set of data?
It was grouped? No.
It was already grouped?
Well, it was like 15 to 25. There's this many people.
Awesome, awesome. Let's get me started on the data set, and we'll show you how to deal with it. And then once you see how to start, you'll know how to finish. So 15 to 25 was the first data set. So this is number 10, I'm guessing, right? Yeah.
It was, yeah.
So you got, remember what the context of the data was for this one?
It was people, let me just look at the book.
And I'll also slide the camera over so you can see.
I don't know, old people.
Old people?
Oh no, it was annual salary.
Annual salary, okay.
In thousands.
So 15 to 25, 50 to 25,000. So this
Yeah.
is salary in thousands of dollars. Okay. So you got 50 to 25. Give me a few more. So 25 to 35.
Up to 65.
Okay, good. And we'll just do a couple of these. Once you see how to proceed with a couple, you'll get the point. Frequencies over here.
Yeah.
Give me the first three.
12, 37, 26.
Awesome. Fantastic, fantastic, fantastic. So this is a frequency, and this dot. Once, like I said, once you see the pattern, people see how to finish it off. So basically, an ogive is essentially a histogram-y thing, but it's on cumulative frequencies versus frequencies. So what you're going to want to do is you're going to want to make a cumulative frequency column. This is like with Max. So when we looked at Max's weight when he was mixed in with all the 99 other kids in that chart, we had the histogram originally, and then we had that ogive, or that cumulative frequency histogram, and those bars represented how many kids were at his weight or lower. So this first one, there are 12, I'm assuming people, 12 people that have salaries between $15,000 and $25,000. So essentially, if you want to say it a different way, 12 people have a salary of no more than $25,000. This next one down here has to be the number of people that have a salary of no more than $35,000.
That includes a 37 and
yes,
right?
And that's why it's cumulative, because what you're going to do is you're basically going to sum this and this to get that. Does that make sense? That's what makes it cumulative, which turns into an ogive, which is a strange word, but that's what it becomes, an ogive. So these guys get added together, and they end up over here with that 49. So that would be there. And then the next one down, you start to see the pattern now. The next one down will be this one plus this one over 2. So I got 26 to that, which is going to be 75.
Yep.
So that's the number of people that make no more than $45,000 a year. And then the next one down, you just add whatever that is to above it, and that's no more than $55,000 and so forth. And that's all. That's the only difference. You would still pick the midpoint the same way. So you'd still say half of it, they call it 20, 30, 40. Remember, like on your last exam when you did if you're trying to graph it.
That's what I'm trying to graph it, yeah.
Yeah, so just in L1, put the midpoints, or are you trying to draw it by hand or use your TI?
No, I was using my TI.
Well, yeah, so in L1, if you would, just put the midpoints of these, 20, 30, 40, because you don't have the raw data anymore. You have to assume that you've got 20, 30, 40. You could call it 25, 35, 45 if you wanted to. But if you want to keep it consistent with what we've been doing, just call it all 20,000, 30,000, 40,000. I mean, if you want to go with the literal definition of ogive, call it 25, 35, 45. That's the right sides of it. And then as far as the cumulative frequencies go, Tabitha, just put those in there. What are you going to notice about the graph once you graph it?
I'll tell you when I graph it.
Well, before you even graph it, you're going to know what it's going to look like, or what it's not going to look like, better yet. What do you think, Athena?
Is it going to be all skewed?
It's going to keep rising, or maybe flattening off. Could it flatten off?
might.
If it flattens off, what do you know would have happened in this column somewhere?
The number started
Go ahead, be brave. They got smaller, and eventually they shrink down to 0. Like, for example, if this next one right here was 0, the cumulative here would still be 75. Because you still have the 75 below it, but you're adding 0 to it, so it'll still be 75. If it got smaller, like you guys are saying, it wouldn't be rising as fast, it'd be rising more slowly. What can it never do? Can't ever go down, unless you're having negative frequencies. It doesn't make any sense. So basically, you can envision what this looks like. It's going to be rising like this, I imagine.
So the slope would basically, I know it's not a word to use.
No, go for it. I like the word slope.
A slope would basically be, it would be just going up. It would be...
On average, increasing. Yes. As you go from point 0 to point n.
So it'd have to be at an increasing rate.
It has to be. Well, can I say it differently?
Okay.
It can't be at a non-increasing rate. Cassie's saying you said the same thing Raphael did. I kind of didn't though. He said it has to be increasing. There's two other things it can be, decreasing or constant. So if I say non-increasing, I covered both of those bases.
Okay.
Is that?
Yeah.
It sounds like a smart ass thing to say.
It's going to be a constant slope. That's going to be...
It could be 0 slope or it could be increasing, but it definitely can't go down.
Okay.
Cool, Tyler, does that make sense?
Yeah.
Good, very good, very good. And I saw some looks of consternation when I said just call it L1 the halfway point. You can also call it the right point, since you're going with an ogive idea. So these 12 make no more than 25,000. I mean, I can totally see it doing that way. It's up to you at that point. If you want to stay consistent to the normal frequency histogram, just call it 20. Please, Chestnut.
How do you do an ogive on here?
Just do it like any other. Oh, if you want to make it a histogram, just use a histogram. If not, use the one right next to histogram, which is it's a histogram with a line instead. So it's choice 2. If you're looking across the top line of your TI, it's scatter plot, then frequency polygon, then histogram. You don't have to know the names. Just use the second choice, and that'll actually be a line versus the bars. Is that fair? But you can just use the histogram, which gets the idea across as well. Chester, that make sense?
Well, I thought the ogive was one where it always goes up to 100.
It does. The only thing, all you have to do, Chester, is make sure you put the data in adding up. The TI doesn't actually do an ogive, it does a histogram. You have to make sure it's cumulative.
Okay.
It's not quite smart enough to do an ogive. They haven't set up to that for us. We have to be smart in the TI, which is all our case fortunate. Yay, us. Cool? What else in there gave you grief? Tab, does that answer your question?
Yeah.
You got this now. You got this. You're all over.
Thank you.
Cool, good question. Anything else give you grief? You got some box plots at the bottom. This is actually what I kind of gave my talk about on Aromatic last week-ish. Oh, there's your answers. You can pull the answers that you want. Cool? Decent? All right, good stuff, good stuff. So I'll throw a quiz up on this stuff for Monday. Yes, Tabitha?
What's the difference between the mid-quartile and the median?
Define a mid-quartile for me.
It is...
Is that the halfway point between the quartiles?
Between Q1 and...
Oh, okay, great question. Okay, so you know what, let's just to have an example. There's some box plots.
And Q2.
Good. Well, which is the median? Tabitha's got a great question, right? Let's pull this up a little bit. So Tabitha's got an awesome question. What is the difference between the mid-quartile, which by definition, let's put that on the board too, your mid-quartile is defined to be halfway between, correct? So if I average Q1 and Q3 and divide it by 2, that's the mid-quartile. So, for example, if Q1 is 7 and Q3 is 11, the mid-quartile is 9. And you can find that very easily by going 7 plus 11 is 18 divided by 2 is 9. That gives you the halfway point. Is that fair?
Mm-hmm.
What's the difference between that and the median, which is Q2? Or another question is there a difference? Is there always a difference? Is there sometimes a difference? Why do you care? Let's answer one question at a time. First of all, is there a difference?
There is a difference.
Tell me why, Raphael. Give me an example or a counterexample up there on the board.
Well, when you're using Q1 and Q2 as a point, what you're trying to do
Well,
is...
Q1 and Q3, you mean?
Yeah, Q1 and Q3, what you're doing when you're dividing by 2 is you're evenly spreading out the data amongst both areas. Right?
I don't have a laser pointer, so I'm going to stand on this chair with wheels. I'm glad this is being recorded. This could end poorly. Let's look at the hands-on throat phone links, okay? There's Q3. There's Q1. Where's Q2?
The line.
The median. Where's the mid-quartile?
Okay.
Wouldn't it be right
Right
here?
in the center of that.
That would be the mid-quartile, halfway between Q1 and Q3.
Okay.
So in this case, they aren't the same number.
Yeah.
How about with power 4? Q1, Q3, who's that?
Q2.
That's Q2.
Median.
Where's the median?
A little.
Or excuse me, where's the mid-quartile?
A little.
It's going to be like here, isn't it? There's plow. Do they look different here?
Looks like
They look kind of the same here, don't they? It looks like the mid-quartile is the median here. How about Van Halen? Right, Q3, Q1, median, mid-quartile. So, conceptually, I don't talk about the mid-quartile too much because it really doesn't tell us a great deal. It does exactly what Raphael says. It oversimplifies the variation in the middle 50%. I love the median, though, because what does the median do? All the time, every time.
Gives us the 50%.
It gives us the 50th percentile. So when you see the median, say, whoop.
Sounds like workers' comp.
Sounds like my spleen just exited my body. So you got Q3 and you got Q2, and excuse me, Q3, Q1, Q2 is right up here. Does this tell me something? And does this tell me something?
Yeah.
What does this being so thin tell me versus this being so wide?
We have less variation.
Yes.
Than the 20 other.
This 25% of songs in the hands-on throw category are very close in length, whereas these 25% are more spread out. That's why I like the median versus the mid-quartile. Mid-quartile doesn't, you lose that. Remember, the tighter these pieces are, the less variation there is. So look at, say that again.
It's kind of like a dense population.
Exactly. Like over here, extreme density here, and then you've got this craziness here. And the reason you have this craziness we're going to talk about today, there's one song that is ridiculously long in this sample, and everything else comes down to here. But you can see the variation by the length of the pieces. The mid-quartile loses that. So I like analyzing the differences of it because the mid-quartile is just one more of those many, many measures that's out there in the world floating around. But it's important to know that just because you average them doesn't mean it's the same. It can be the same. It can be, but it doesn't have to be, as we just saw with the box plots there. Great question.
How long is Stairway to Heaven? I can't
3.5 days, give or take.
Yeah, I'm like,
Orion
I
is
don't think
like
it's enough room.
Orion is like 9 minutes.
Is that the
Yeah. Well, No Effects wrote an album that's one side of the entire song, 22 minutes or something. Every Dream Theater song.
Ridiculous.
Every Dream Theater. They're all awesome. They're all so very long. So.
I understand that there's outliers that are out there, right? And that's the whisker. But
Well, let's continue that discussion.
yeah, it's really weird. Yeah.
What were you?
It's still kind of gray about the outliers.
Good. Well, first of all, realize this. Thank you, Raphael, for a perfect segue, by the way. First of all, do you hear what Raphael just said? He said one thing. He said, first of all, I understand that the outliers are out there in the whisker. Okay, first of all, yes, if there are outliers, they will be out there in the whisker. But then Lucas followed up with, you followed up with a beautiful statement. You said,
I said, well, what's an outlier?
what is an outlier? That was a beautiful statement. What is an outlier? Define what an outlier is. Yeah, if it's going to be out there on the whisker, if it's an outlier that's too big or too small, it's going to be out in the whisker, but what even is an outlier? Let's come back to that and talk and pull up some data from yesterday, which was the height data that you guys gave me. Now, Charlie brought the projector back, which is great. If I can use it. Got a fire machine up on the computer. So you guys locate your height guesses for me from yesterday? Remember those? Indeed. Of course, you plug it in first. I just love it up here. There's so much potential for mass injury. Cords, rolling chairs, me.
Yeah.
Just me in general. The fact that I'm here. All right, so I got an editor.
Yeah, it's like 5 minutes.
This is you guys, right?
Yeah.
So 3 of you guessed 69 inches, 4 of you guessed 70, and so forth and so on. Okay. So let's start by getting a look histogramically at that data. Okay, histogrammy at that data. So make yourselves a nice histogram of L5 and L6. Make sure you can see this in the camera. Okay. So. I just turned plot 2 up. Oh, and this, speaking of which, thank you, Tabitha, for mentioning that.
Well, I didn't say any
You did. You said, how did you? You said, how did you, as I was turning off plot 2, and that reminded me, in the earlier 243 class, there were a bunch of errors that were coming when folks were graphing. When you have 2 plots on, sometimes if you change your data, but you forget to turn your plots off, you can generate stat errors and dim errors and things like that. So just realize that if you get stat errors, make sure your plots aren't trying to plot something that isn't there anymore. Like I have to change my list to L5 and L6 now. So there we are. A little zoom stat. Oops, that was the wrong button. Zoom 9. All right, there we are. And I'm going to change the scale of 1. The highest guess was 73. 73, so I'm going to make that a 74. 69 to 70, right? This will look pretty decent. Okay, that's not bad. That's not bad at all. Ooh, goodness.
And when you get invalid dim, what do you fix that?
That's exactly what I'm talking about. Chances are you're trying to graph a list that isn't there anymore. So make sure that your plot is pointing at the list where your data is. Cool? All right, so now we're going back to Sean, your Sean's height guesses. Okay, and you know what? While we're here, let's get some statistics while we're at it. One of our stats on L5 and L6. You guys averaged about a 71-inch guess, plus or minus about a 1-inch. And the median's down there at 71 as well. Actually, just 71. So your median and your average are just about equal to each other, which doesn't tell me anything about the distribution until I look at the distribution. And then I can maybe get a better idea about the shape of the distribution. If you had to pick a few words to describe the distribution of your guys' guesses at my height, what words would you use? What words would you use? If you had to describe that shape. What kind of words?
It's
Shape of the data.
somewhat bell-shaped, right?
I call it bell-shaped for a couple reasons. I mean, it's got
Pretty much.
Good. It basically has an overriding. Listen. You've got this overriding bell shape. It's got a hiccup over here, but again, a fairly small sample set overall. Fairly small. But it's got the most of the data in the middle. You've got this chunk of data in the middle. The question I have is this jump out here like significantly atypical? This is going back to what Raphael and Lucas were pointing out. Like, okay, if there are outliers, where are they? So yesterday we talked about one method of finding outliers that works only when your data is bell-shaped. And I should say it works consistently only when your data is bell-shaped. Go ahead, Raphael.
That's when you use, within two standard deviation points will give you 95%.
Exactly, which means atypical. Very nice, my friend. So let's put this, we'll put this right here.
If it's atypical.
We'll say outlier ID. And these are humanly created rules. This isn't like gravity. What I'm so excited about is we're just about ready to start probability in this course, like the formal discussion of probability. Probability is governed by laws, like laws of mathematics. We talked about this a little bit 105 last term. Like when you roll a die, the 1/6 actually means something that's observable over time. These outlier rules, the definition of means and medians and standard deviations, they're all created by people. They're not laws, they're just definitions. So when we talk about what Raphael just said, method number 1, we'll call it the 2 standard deviation method. Basically, what has been set up is typical data is within 2 standard deviations of average. So basically, when you look at that bell curve and you slap up 2 standard deviations, you say, okay, that's where typical is. And then we kind of do this automatically anyway. When you guys called that bell-shaped data, you looked at it and you said, okay, the bump's in the middle, it tails off. And once you get too far away from that bump in the middle, that's where the interesting stuff is happening, too small or too big. And more on what I mean by interesting momentarily. And when I say momentarily, I mean like an hour from now. We'll get to that eventually. I want to make sure we quantify these outliers first. So if typical data is within 2 standard deviations, that means atypical is outside. Atypical's outside. So our job is just to do a quick check on x bar plus or minus 2s, form two standard deviations, form the range of the values that makes two standard deviations, and then see if there's any data that pops in or pops out of that. Make sense? Well, let's do it. Here's our data. Here's our data. Right? So x bar plus or minus 2 standard deviations gives us the range of values. Well, x bar is 71. S is 1 inch. 1 inch. So this is going to be 71 inches plus or minus 2 inches, which will drop us down to 69 inches and up to 73 inches. So essentially, what that tells us is, as long as you're guessing between 69 and 73 inches, you're considered a typical data response. And guess what? What happened with our data? All of you guessed within there, right? Every single one of you guessed within there. So therefore, we don't have any outliers by that definition. You don't have to have outliers, which comes back to Raphael 10 minutes ago. You said, I know the whisker shows the outliers. It can show the outliers if they're there, but just because it's a whisker doesn't mean it's unusually large or small. It just means it's the largest and the smallest. That doesn't mean it's unusually large or unusually small. It's like, I had this discussion today with Charlie, the guy who was just in here. He was talking about remembering a class he took 25 years ago with a colleague from a different community college. She remembered the instructor being 6'8". And he was like, dude, no way, not an inch over 6'3". It was a hilarious conversation to have. That's both very tall. But 6'8" is much, much taller when you adjust it for the standard deviation of 2.5 inches that adult males actually have, which we'll study later on this course when we get more to the normal distribution. Every standard deviation on adult males bops out 2.5 inches either direction. So you start at average, go out 2.5, so you go out 5. Then you go out 2.5, 2.5, 2.5, 2.5. Going from 6'3" to 6'8", you've actually gone 2 standard deviations more. That is significant. That is significant. Because think about it, 1 standard deviation, 68%. Then 95%. You're picking up a lot more data going out that way. If you've gotten outside of even 1 more standard deviation, you've left the vast majority of data points behind you. Which means your data point is exceptionally what? Is exceptionally what? Good, atypical, it's unusual. It shouldn't have happened, but there it is. 6'8", it's a huge dude. There's a band called Flatfoot 56 from Chicago that stayed with me. They were coming through on tour. The average height of that band was like 6'4". They have a song called 6'10", which is about the lead singer getting tired of being asked how tall he is. So he wrote a song called 6'10" to answer the question. 6'10". I'm basically 5'10". The dude's a head higher than me. I mean, these are big dudes, and 3 of them are brothers, so there's the genetic tie right there. Huge, huge. But they're outliers, a full band of outliers. Bagpipes, which is even cooler. The bagpiper's 5'11". He looks short next to him. He's 5'11". He's a bagpiper. They're a Celtic band. Okay. So anyway, cool. Now you can also, if you want, you can also crunch these numbers using the variable shortcuts from your TI. There was a quiz I gave you a couple weeks ago on a variation. There's a series of button pushes where you could. Let me just show you, and you can also tell me if you didn't like this when you did it. I've run 1 bar stats, right? Yeah, I did already. So do you remember a quiz a couple back in the VARs menu? There are statistics variables in there.
Yes.
And you can actually call x bar plus 2 s's. And you can actually see how we called it 73, but this is the unrounded version, if you will. And then you can back it up and make it x bar minus. And then you get that. So you can also do this completely in your TI. Did anybody do that and enjoy it?
Yeah.
Okay, we did it great, or we didn't hate it. So just so you know, there are shortcuts. Your TI's got tons of shortcuts buried in, and that's all in the quiz from a couple weeks ago. So if you want to see it, you can refer back to it.
I did it different. I was like bars 52.
Perfect.
Bars,
Right. Exactly.
bars
Exactly. Because your point.
53.
Totally. Exactly. You can get to the same place different ways for sure, but it's all buried in there. Or you can just round them off and do it this way. The reason I like doing it the TI way is every time you round in an intermediate step, you introduce error into your calculation. So if you round and you just keep nesting results, you end up creating more error than you should technically have. So the less rounding you can do before your final result, the better. Yay! So there we go. All right. So what we need is now a way to generate outliers when data is not bell-shaped. Because we've gotten 2 great data sets where data is bell-shaped. My height, my weight. So let's generate some atypical data. How many text messages have you sent today?
What kind of question is that?
It's one that's going to generate some skewed-ass data.
Yeah, it is.
How many text messages? I don't know.
You check, I don't know.
Well, just check the date. They should be listed by date,
How many
right?
people, yeah, just look in the last,
To people or specific like
All of them
actual
together.
messages? Or just
How many,
people?
how many I've made, or how many I've made and received? or
Oh, man.
How many times have you pressed send on a text message?
how many times
How about we
I've
define it like that?
sent on a
Yeah.
text message?
I've never had this much animosity towards this question before. My goodness. Go, okay, good. Let's collect some data. Let's collect some, put it over here. We're going to take the salaries out of here. We do. We need data. We do. So go collect your data. Let's get this data set collected, and then we'll analyze it after the break. So